today we are planning to cover a new section we are planning to talk about isoparametric formulation in finite element method. What is the motivation behind this isoparametric formulation? Yeah, so first let's try to understand the term isoparametric. So with the term, what do you think the term means, isoparametric? Isoparametric, as the term denotes, iso means single. You use a single parameter to express, let's say, certain functions within a finite element formulation. So the motivation is, as you saw during the previous lecture, where we discussed the derivation of the stiffness matrix for a linear strain triangular element, we saw that it's quite cumbersome. It contains a lot of lengthy equations, and we need the help of a computer, of course, to solve these large matrices, and of course this development of the matrices and also the equations when with reference to the global coordinate system, it becomes an enormously difficult task to solve even the simplest problem. Let's say even a problem having one or two elements. Even if we consider the constant strain triangular, if it is slightly less complex than, of course, the linear strain triangular element, but we saw there's a difficulty when we use a global coordinate system. Element matrices. So element matrices and equations expressed in terms of these element matrices becomes difficult to solve when they are expressed in global coordinate systems. The equations become lengthy, the matrices become large, so it's quite cumbersome to calculate even for a, let's say, single, let's say, few elements. And we would also like to have kind of like a simple, let's say, method which is also compatible when it comes to solving finite element based problems using computer programs. If we are able to get a good formation of the problem which is also compatible for computer programming, then it's much better, isn't it? So in this connection, we are planning to use, or we intend to use, the isoparametric method in order to kind of like kind of simplify the whole scenario, so that it will be beneficial for when we think in terms of computer programming also. Initially, it may appear to be quite tedious, or maybe you may realize, okay, this method, the isoparametric method, is somewhat even more complex than the general formulation method when we use global coordinate systems to express the system of equations. But later onwards, you will realize when the problems get complex, this method comes really handy, and it makes the life of the, let's say, computer programmer as well as the computer program to solve these problems. And these problems in 2 and 3 dimensional stress analysis, also structural as well as non-structural problems, can be easily tackled with mostly non-structural problems can be tackled with this type of formulation. The focus is mainly on, let's say, 2-dimensional as well as 3-dimensional problems, mostly non-structural elements, because these isoparametric formulations allow to create, let's say, elements which are, let's say, non-rectangular, and we can also employ elements having curved surfaces. So non-rectangular elements, also including curved surfaces. So you may have realized from your experience which you have gained during the lab sessions, that the more complex the geometry that you're trying to simulate, or that you're trying to model via finite element method, you will realize that it is important to introduce elements which can mimic the exact geometrical shape as well as elements which are quite suitable for proper boundary condition. Yeah. So having with that intention, sometimes it can be the case that you will not be able to use simple beam elements, simple bar element, linear constraint, triangular elements. You might need to linear constraint, linear CST element, linear constant strain triangular elements, or linear strain triangular elements. You might need to use more complex elements, or having large number of nodes, large in higher order elements. You might need to use higher order elements to properly capture a certain, let's say, if it is a stress distribution, of course, such elements might be required to capture stress distribution accurately when using higher order elements. So when you're using higher order elements, the systems or the set of equations behind the finite element formulations, especially when you're using a global coordinate system to express this, becomes complex. That is why we use isoparametric formulation to solve this, let's say, to make our life more easier. And also most of the commercially available finite element based simulation programs have incorporated this isoparametric formulation of finite element based problems into the commercial packages. So it's quite important to know what is really happening when we use this method. Even though we use this method, let's say, to solve higher order elements, something like complex elements like quadrilateral element, this method will be quite, of course, when we use such high order systems, then only we will realize the importance of this method, how this method becomes computationally quite efficient. But in order to get an understanding of this method, it's important to look at a simple bar element. Let's say, let's try to derive the simple, consider a bar element stiffness matrix and try to develop it using isoparametric formulation, yeah, to get a hang of this system, to get a clear understanding of what's really happening behind this system. So first, let's consider a bar element matrix. Let's consider the isoparametric formulation of a bar element. Let's consider a simple bar element first, okay? So as I mentioned before, the isoparametric term, or the term isoparametric, is derived because we use the same parameter, let's say, so to say, to express the displacement of, let's say, nodes of a certain element, as well as to express the shape of the element. So the previous case, if you can remember about the B matrix that we described, which is a function of the local coordinate systems, and it kinds of describes the shape of the element. So this shape of the, so in this method, in the previous method, we used the global coordinate system to express this, and of course we came up with a shape function to derive the displacements within the element. So now what we do is we use the same function, or in other words, interpolation function, which is denoted by capital N. So we use this shape functions also to determine the geometric shape of the elements. So we will not be using global coordinates, but we will be using these functions, let's say, and introduced, let's say, a reference system, or we will be expressing the geometric shape also using these shape functions. In other words, if we assume a shape function for displacement, let's assume a shape function given by u, and as you know, there are coefficients based on the nodal degrees of freedom. There will be a certain amount of coefficients which will appear in the linear function. If it's a linear function, of course, which you have to find out, and we express in terms of a, let's say, let's call S a natural or an intrinsic coordinate system. So let's say u, we express it as a function of s, and of course we can also use this coordinate system for describing the nodal for example, to describe the, let's say, the shape of the element. That is, when you describe the nodal coordinates, of course we can use this same kind of function to describe the shape of the element, the physical shape of the element. So you know, the displacement function or the shape function or the interpolation function describes the displacement within the element, displacements within the domain, isn't it? So we use the same kind of function. We call this as this both type of, let's say, in the isoparametric formulations, these element equations are formed using a special coordinate system. We call it a natural coordinate system or intrinsic coordinate system. So this, unlike the global coordinate system, this intrinsic or the natural coordinate system is not defined by, let's say, the element geometry or the element orientation, of course, in the global coordinate system. So this natural coordinate system does not depend on the geometry of the element or the orientation in the global coordinate system. So you will see what I mean by this. So in this coordinate system, usually the axial coordinate, as in this case, is generally defined. When we think in terms of a simple bar element, it is defined along the axial length of the bar. And it is irrespective of how this bar is oriented in space. So as you may have realized now, what we do is we do a certain mapping. Yeah, we call it a transformation mapping. So what we do in this method is we do a transformation mapping, yeah, from, let's say, the global coordinate system to the natural coordinate system. Let's call it x and y. We can call it s and t. If it is a single, if it's an axial element, just like the bar element that we will be discussing, we need only x term, and x will be mapped to the s coordinate system. So it's kind of a like transformation from one domain to the other domain. You can also think, because let's say maybe in controls engineering you may have already learned, now you move from the time domain when the things get complex, or when the math, or when it's hard to deal in the time domain, you move on to the frequency domain, because the frequency can be added, subtracted quite easily. So you would move from, let's say, by moving from one domain to the other domain, you get certain advantages. That is the advantages. That is the reason you move from, let's say, time domain to frequency domain to solve different problems. Similar to that, of course, we are still in the spatial domain, but we do kind of like a mapping from the global coordinate system to a kind of like a natural coordinate system. So we do a mapping of the two, between the two coordinate system. So let's try to develop, let's say, the isoparametric formulation. Okay, let's try to develop a stiffness matrix using the isoparametric formulation for a simple linear bar element. This is what our topic denotes, isn't it? Isoparametric formulation of the bar element stiffness matrix. Let's consider a simple bar element. We can define a bar element having only two nodes. So in the if we use the global coordinate system x, yeah, we can define x1 and x2 to define the nodal coordinates for the bar having a length L. X is the coordinate system and U is the displacement, nodal displacements when we use the x-coordinate system. So now what we do is we do a transformation. So we move from the global coordinate system to a new coordinate system, the natural coordinate system. Let's say from global to natural. How can we define this natural coordinate system? We have two nodes, of course, and we already selected that we will be using the term S to define our natural coordinate system. If it is a single parameter, of course, a single coordinate, then what we do is we select this coordinate system such that the origin is located at the very center of the element. So let's select this coordinate system with reference to the material, of course. At the center, the origin, where the origin is located, the S value becomes 0. Let's call at, let's say, for the simple bar element having a length L, node 2 would refer to, let's say, a coordinate of S coordinate having the numerical value 1, and on the left hand side, the node 1, the S coordinate will refer to a numerical value of -1. So we have mapped x1 and x2 to S values, that is from -1 to 1. It's kind of like you map them, map the distribution or the variation to a certain identified domain. So, and it's, even though I have used the formulation like this, the coordinate system, let's say the natural coordinate system, the x-axis need not be parallel to the x-axis, and I have only used it for the convenience. These S and Y need not be parallel, of course, need not be, of course, they are not coinciding there. So you can arbitrarily select, as I mentioned before, this natural coordinate system does not depend on the element shape or the orientation of the element, so that you can decide according to your wish. But only for this problem, I have used a parallel, selected it to be parallel to the x-coordinate system, just for simplicity. So since we consider a bar element having 2 degrees of freedom, what would be the axial displacements corresponding to, let's say, x corresponding to x1 and x2? The axial displacements would be u1 and u2, which is associated with each node for the when we talk in terms of the global coordinate system. Since we have selected these 2 coordinate systems, of course, which are parallel to each other, we can now try to find the relationship between these x values and the s values, or the x coordinate system and the s coordinate system. Meaning, we should be able to go back and forth from the 2 coordinate system. If we substitute corresponding value, let's say, and the x1, the coordinates corresponding to the node 1, we should end up in getting -1 in the s coordinate system. So we want to establish a relationship between the 2 coordinate system. How can we do it is, we can express the relationship between the 2 coordinate system using this equation, that the relationship between the global coordinate system and, of course, the natural system, you would be able to get it using this equation. Let's call it 7.11a. So xc is, of course, the global coordinate, of course, of the element centroid. Based using these global coordinates, let's say x1 and x2, and using this equation which I have just written, which maps the global coordinate system to the local coordinate system, we can of course express the natural coordinate system, or S terms, in the global coordinate system using the values which we have used in this problem. That is, using x1 and x2 values or let's kind of like the boundaries in the global coordinate system, we can express the natural coordinate system. And when we use the equation 7.1.1a, you can substitute x1 value and x2 value and express the relationship between the s terms and the x terms, meaning the natural coordinate systems and the global coordinate system. And if you when you solve it, you can do it on your own and check. You would be able to get a relationship given by this equation x minus x1 plus x2. These are the coordinates in the global coordinate system, times 2 divided by x2 minus x1. All right, let's call it 1.1.1b. We can now define a position in the bar element, just like what we did in the previous sections. We can use the natural coordinate system and of course define a global coordinate by using let's say this equation that we already wrote down in the first place, which we would like to have, because now we know the relationship between the two coordinate system. Now we would like to use, because this is isoparametric formulation, I mentioned you before, we will be using the same parameter, or we will be using, let's say, the shape functions described using the natural coordinate system to express the displacement within the element of displacement of the nodes, as well as the shape of the element. So the shape is given by, let's say, such a function, and this function is such that the term s is bounded within these two values, -1 and 1. And of course now our aim is to find out the a values, that is ai, in terms of this x1 and x2 values, isn't it? So since we already know the two coordinates, two nodal coordinates, of course we can substitute the values, and since we already know the relationship, we can express so our idea is to find a1 and a2, so that we find the relationship between the shape of the element as well as the natural coordinate system. So by substituting, let's say, x1 and x2 coordinate values, we establish the same relationship. You can obtain it, of course, using this by solving equation 7.1.1b. By solving x, you would be able to get x equals to half times 1 minus s. Now the terms in the natural coordinate systems appear, and also it is expressed, mind you, x1 and x2 are just simple numerical values. You will be able to express in terms of, let's say, the natural coordinate system. Or in the matrix form, you can simply write down this equation. X is nothing but the shape of the element, and interestingly, you would like to express this in terms of course, the global coordinate system. And what do we get? Since we are using the isoparametric formulation, we are able to separate it to shape functions, n1 and n2, defined by the two shape functions corresponding to the two nodes. So the shape function of these equations are given by, if you use this equation 7.1.3 and separate the two matrices, you would get the shape functions n1 to be 1 minus s divided by 2 and 1 plus s divided by 2. So you see we have used two linear functions to map s coordinate of any point, of course, in the element to the x coordinate, which is described, of course, in the global coordinate system. If we have done the arithmetics correctly, when we substitute, let's say, an x1 value to this equation, we should get the corresponding local code, the natural coordinate as s minus 1 in the natural coordinate system. And if we substitute x2 into this equation, we should get 1 for the s value, if we have done it correctly. And since these are expressed via shape functions, all the properties which correspond to shape functions are also applicable in this case. So meaning n1 generally represents, or of course it represents the physical shape of the coordinate x, which is when it is plotted over the element, meaning the shape function would be 1 at node number 1, and it would be 0 at all the other nodes, meaning at node 2 it would be 0. Similarly, n2, the shape function, when it is plotted over the length of the element, it would be 1 at node number 2, and of course 0 at node number 1. And when you add these two shape functions at any point within the domain, it would be equal to 1. So these properties corresponding to the shape functions would still be applicable, of course, are also relevant in this case. So just to get an idea, let's try to see how these shape functions vary within the natural coordinates. Let's try to write down, let's try to plot the shape function n1 using the natural coordinate system. So in the natural coordinate system, if n1 is a shape function which we are interested in, S defines the local coordinate system or the reference, the natural coordinate system, and the term n1 at the node number 1 and 2, we know it should the S value should correspond to 1. These are the node numbers, so I'll write down, put 2 circles around it. At the middle, it should be 0, and at the left-hand side, it should be -1. And what is the value of the n1? At node number 1, n1 should be equal to 1. At node number 2, the n1 should correspond to 0. Similarly, we can write down the shape function for n2. For shape function n2, again, we define the coordinate system, and we know that at node 1, the shape function should correspond to 0. At node 2, the shape function should correspond to 1. N2 is what we are interested in, and we are looking at the variation in the natural coordinate system. Node number 1 and node number 2. At node number 1, n2 is in. At node number 2, where the s value corresponds to -1, the value of the n2 or the shape function n2 should correspond to 1. And we know this function, n1 function, is described by this term 1 minus s divided by 2, and n2, the shape of this function is defined by n2 is equal to 1 plus s divided by 2. Now, when we think in terms of the displacement along the length of the element, this is how it would look like. The natural coordinate system, we are interested in that, not the shape function, of course, but the total displacement now within this domain. So let's define u, and the s term here, of course, the s coordinate system. So now we know the displacements are bounded by 1 and -1 to node 2, node 1, and the corresponding displacement at node number 1 is u1, and the displacement at node number 2 is u2. So the displacement within the domain is nothing but linear function described using, if you can remember, using the shape functions. So now our attempt is to so this is kind of like a step one, yeah, because in the step one we selected the element type. Maybe I forgot to write it down. Again, we will be going through the same number of steps which we uh, already went through when we derived different types of element matrices. So when we are applying the isoparametric formulation, also we will, the same protocol is the same. We will be going through the same amount of steps when we are deriving the applying the isoparametric formulation for this simple bar element stiffness matrix. So step one is the selection of the element. Selection of the element. We selected a simple bar element, and of course defined the displacement as well as the shape of the element using a natural coordinate system. Once we define the displacement, of course, we express once we selected the element and of course describe the element using the coordinate system of interest. The next step is to select a proper displacement function.